Hello everyone. In this lecture, we will be discussing about graph traversals, two graph traversal techniques, breadth first search and depth first search. We'll start off with breadth first search. These are actually similar to tree traversal methods. We will see one by one. Let's take this example graph with 7 vertices. The idea behind BFS, you can see that it is similar to level order traversal of a binary tree. We can actually convert this graph into a tree. We may not be getting a binary tree, but we'll be getting a tree. Let's try to convert this into a tree first. Then we'll look at breadth first search algorithm. Let's begin with the vertex 1. Vertex 1 is having edges 2, vertex 2, vertex 3, and vertex 4. So these edges have been considered, and these vertices have also been considered. So vertex 1, 2, 3, and 4. In the next step, it's very similar to the level order traversal. In the next step, so the direct edges that are going from 1 to vertex 1 have been considered. So this vertex is visited, this vertex is visited, and this vertex is visited. Now we'll consider the second vertex, vertex 2. Vertex 2 is having an edge to vertex 3, which is 2 to 3. 3 is already being considered, so we can discard that edge. Now let's consider vertex 3. Vertex 3 is having edges to vertex 1. 1 is already considered. Vertex 4. 4 is already considered. 4 is already taken here. Vertex 5. So 5 is a new vertex. So we'll take that vertex, vertex 5, an edge and a vertex 5. So by this, what we are going to do is we are going to transform this graph into a tree by removing the cycle forming edges. Now we'll consider vertex 4. 4 is having edge to 5, 3, and 1. 5, 3, and 1. All these have been considered, so we will not take that. 5 sorry, 4. 4 to 5, this edge is not required. 4 to 1, 4 to 3, these edges are not required. The next vertex that we are going to consider is 5. 5 is having two vertices connected, 6 and 7. Now we'll take 6. 6 is connected to 5. That's already considered. 7 is already considered. So 7 is connected to 5. That's also considered. So we have successfully transformed this graph into a tree. And you can see that this we have done with the help of level order, similar to level order traversal of a binary tree. So this is how we do the breadth first search, that is very similar to level order traversal. You can see that this is not the only possible BFS solutions. There are other possibilities like, for example, if you start off with, instead of starting from vertex 1, if you start from another vertex 4 initially, there is no restriction that you need to start from vertex 1 only. So you can start with vertex 4 also. If you start with vertex 4, you may get a tree like this. Now we'll actually define the breadth first search algorithm. Breadth first search can be defined by using two terms: visiting a vertex, and exploring. Exploring is visiting all the adjacent vertices of a vertex. Initially, we have started with vertex 1, so we have visited it. Then the next step is exploring. Exploring means the adjacent vertices of 1, 2, 3, and 4. Visiting all the adjacent vertices of vertex 1. That is what is meant by exploring a vertex. So by these two terms need to be understood: visiting a vertex and exploring a vertex. For executing breadth first search algorithm, we need something. We need a queue data structure in between. So initially we start off with, let's start off with vertex 1. we have visited it. That is what written here. BFS visited 1. Then we enter 1 onto the queue. Then the procedure is recursive, or the procedure is we can iteratively run this procedure. Now we delete the element from the queue and we find out all the adjacent vertices which are connected by this vertex. Then we'll go for the procedure again and again. So let's see that. We have deleted the entry from Q1 and we found what are the adjacent vertices or exploring. So this is the step in exploring the vertex 1. While exploring the vertex 1, you are supposed to visit 2, 3 and 4. These are the adjacent vertices. 2 is an adjacent to 1, 3 is adjacent to 1, 4 is adjacent to 1. So these 3 vertices are visited. Now while visiting, these need to be considered again. So we need to enter these things into the queue. So while exploring 2, we will visit that, then enter into the queue, enter into the queue, enter into the queue. So 3, 2, 3, 4 are entered into the queue. Now 2 is deleted from the queue and explored. So whenever we visit a vertex, we will enter that node onto the queue, and whenever we explore it, or when once we would like to explore the vertex, we will remove it from the queue. 2 is removed from the queue. While exploring 2, what you are going to get is 3 and 1, which are already visited. So if the vertices are already visited, we will not consider it again. While exploring 3, you will get an additional entry 5, and that is entered into the queue. So in the queue now we have 4 and 5. While exploring vertex 3, you will get additional vertex 5 which will be entered. While exploring 4, we will not get any additional vertex. While exploring 5, you will get additional vertices 6 and 7. So 6 and 7 added. Now exploring 6, there is no more additional vertices or edges. While exploring 7, there is no more edges. Once the queue is empty, then you can stop and you can return this. That this is your breadth first search result. 1, 2, 3, 4, 5, 6, and 7. This is your breadth first search result. This is the order in which you are going to visit the nodes in the case of breadth first search. And this is not only the order in which you are going to visit. If you start off with some other vertex, then you may get some other order in which or another BFS tree. So there is no unique BFS tree based on the consideration. For example, you have entered these into the queue in 2, 3, and 4 in that order. If you have entered into the reverse order 4, 3, and 2, then you may get another queue and so another BFS result and so on. Let's quickly look at breadth first search algorithm. Into the BFS, we are passing the initial or starting vertex. Let it be I. Now you print I, which is same as visiting the node. So, and we'll mark it as visited I equal. We need another array which is having the same size as that of the number of nodes in the graph, and we'll mark it as visited I equal to 1. Then we'll enqueue the entry onto the queue. We'll enter them into the queue, and we'll execute this while loop until queue is empty. You remove the first node from the queue, then we will check whether AUV is equal to 1, whether there is an edge. We are using adjacency matrix representation here. If AUV is 1, means there is an edge between U comma V. And visited V equal to 0 if it is not already visited. If the vertex is already visited, then we'll not consider it. Otherwise, we'll consider it. And printf V. V is visited, and we'll mark it as visited V equal to 1. Then we'll enter onto the queue. Then the while loop is continued, and this loop will be continued till the queue is empty. So the BFS procedure is very simple. You will be passing an initial or starting vertex. We'll mark it as visited. Then we'll enter onto the queue. Then we'll run this while loop. Iteratively, once you run this while loop, you will take one element from one entry from queue. You will find out all the vertices in the level order corresponding to that. Then You will visit all these vertices, new vertices which you are getting, enter these things into the queue, continue the procedure until the queue is empty, and this is the result you are going to get. If you give this graph as an input, then you are going to get this result. So that's about BFS algorithm. Next, we'll look at depth first search or DFS. Depth first search is similar to the pre-order traversal of binary trees. You need to understand two terms related to DFS, visited and exploring, very similar to the BFS algorithm. Let's take the same example, and let's do the DFS procedure first, then we'll explain the DFS algorithm. We'll start off with vertex 1 and we'll mark it as visited. 1 is visited. Here we'll use a stack data structure in between. So while considering 1, we'll mark it as visited and the stack is empty. Now we'll find out all the adjacent vertices to 1, 2, 3, and 4, and we'll enter those things onto the stack. Enter those things in the sense, enter 1 onto the stack, because we have considered 1, then we have 2, 3, and 4. Just like BFS, we are not going to consider 2, 3, and 4 altogether. We are going to consider one node at a time. For example, we'll consider 2 at a time, initially 2, then 3, and then 4. So while considering 2, we have other vertices or other edges which are connected from 1 which need to be considered. So we'll suspend the execution or exploration of 1 until the completion of 2, and so on. So let's see this. 1 to 2, there is an edge. So 2 is visited. Now 1 is entered onto the stack. Exploration of 1 is suspended until the completion of 2. So you will get 1 to 2, this sort of a tree, a subtree. Now from 2, there are edges 2 to 1 and 2 to 3. So we'll check 2 to 1 is already this is already visited, 1 is already visited, so we'll discard it. 2 to 3, there is an edge, so we need to consider 3. So here 3 is also visited and 2 is entered onto the stack. Execution of 2 is suspended until the exploration of 3, and that's how we continue our procedure. Now we consider 3. 3 is already visited. 3 to 4, 3 to 2, 3 to 1, 3 to 5. These many links are there. So let's take 4, 3 to 2, and 3 to 1. These links are already considered. So we'll take 5, 3 to 5 first. Okay. We'll consider this link 5 first, 3 to 5. Right. So 3 to 5 is considered and 3 is entered onto the stack. Exploration of 3 is suspended. So 5 is also visited. Now from 5 you have links to 4, 6, and 7. So exploration of we were at 5, and now let's say we have considered this edge 5 to 7. 5 to 7 we have considered. So 7 is included. 7 is visited. Then we checked with the 7, there is no more edges, so we'll go back and resume the execution of exploration of 5. So you'll get 5 to 6 and one more edge. So 6 is visited. Next we will go back and we'll continue the exploration of 5 again. 5 to 4 we'll get one more, so we'll add 4. So 4 will be exploration of 4 next. Exploration of 4 in the sense there is no more edges to be considered. So we'll go back. Exploration of 3 is resumed. So there is no more edges. Exploration of 2 is resumed. So at last your stack will be empty. So 3 will be removed, 5 will be removed, 3 will be removed, 2 will be removed, and 1 will be removed. The stack is empty. Once the stack is empty, you can come out of this loop, and you can say that this is the structure you are going to get, or this is the tree you are going to get. We call it Dfs Spanning Tree. This is the tree you are going to get on depth first search. If you ask, is this the only tree you're going to get? No, you can start off with another vertex and you can get another tree, or you can consider these vertices in different orders. Instead of starting after 1 to 2, you can start off with 1 to 3 and you can get another tree. For example, there are other possible ways, like you can have other valid DFS traversals like 1 3 5 4 7 6 2, 1 2 3 4 5 6 7, and so on. So many other DFS traversals you can get. The tree structure which you are going to get, which you are getting after a DFS successful DFS traversal, is called a DFS spanning tree. Total time taken, the analytical time taken for a DFS traversal is order of n. We need to visit all the vertices once. That's it, isn't it? So the number of vertices, that's the total time taken. But in the case of real implementation, it may take more time, because if you are using adjacency matrix representation for your graph, then it may take order of n square. If you are using adjacency list representation, it may take order of n plus e number of times, etc. So in implementation, this is just analytical time, and in implementation you may get it may take more time. Now let's look at DFS algorithm. Into the DFS algorithm, we are passing once again the initial vertex. This is a recursive algorithm. I have written a recursive algorithm here. If visited u is 0, here also we require a visited array corresponding to the number of elements in the uh, number of vertices in the graph. You visit the vertex u, make it visited in the array. Then if AUV equal to 1, if there is an edge and visited is not equal to 0, if it is not visited, then only you call again DFS with this vertex. So there is no need to internally use a stack, etc. here, because here in the recursive call itself, the stack, etc. will be internally managed. So you call it by using, for example, you are starting with vertex 1. Vertex 1 will be printed, then vertex 1 is visited of 1 equal to 2. Then from 1 to n, if AUV equal to 1 and visited is not equal to 0, you call it with that DFS. So let's say 1 to 2 itself is 1. 1 to 2 is 1, so DFS 2 will be 1. Then DFS 2, 2, and so on. So this for loop will be suspended till the execution of DFS 2, and the DFS 2 will invoke another for loop which will be suspended until the execution of DFS 3, and so on. So this is about the DFS algorithm. So in this lecture, we have seen breadth first search and depth first search. Breadth first search is very similar to level order traversal in the case of binary trees, and depth first search is similar to pre-order traversal in the case of binary trees. Thank you.